Hi everyone. Today we're going to talk about work-efficient batch-incremental minimum spanning trees with applications to the sliding window model. I'm Dan, and this is joint work with Blelloch and Kanat Tangwongsan. So what we'll talk about today, we'll first go over some useful preliminaries. We'll talk about the incremental MST problem, what it means, and the classic sequential solution. And then we'll go over a key ingredient in the design of our parallel algorithm, which is parallel tree contraction and parallel rate-compress trees. Then we'll go on to our main results. We'll talk about batch-incremental MSTs. An ingredient that we use to develop our algorithm is a data structure called parallel compressed path trees. We'll talk about these, and then we'll see our main result on batch-incremental minimum spanning trees. Then we'll finish up by talking about some applications. We'll show you how you can use these tools to design algorithms for sliding window dynamic graph problems in the parallel setting. So first of all, the incremental MST problem. We're given a graph. It's a weighted undirected graph. We'd like to maintain its minimum spanning tree while supporting the operation addEdge, which allows us to add a new edge into the graph. Every time we add an edge into the graph, we may or may not need to update the minimum spanning tree. This can be done in log n time per update using link cut trees by Slater and Tarjan. In the parallel setting, it gets more interesting. We can start to talk about the batch incremental setting. So similar idea, we're given a weighted undirected graph G, but now the updates, instead of adding a single edge to the graph, the updates now allow us to add a batch of many edges to the graph all at once. And the goal is still the same. We want to maintain the MST by updating it every time new edges are added to the graph. And our overall goal is to design an algorithm for the batch incremental case whose work is no more than had we just inserted the edges one by one using the single update algorithm. So while there are many parallel algorithms for the batch incremental case already, none of them achieve this goal that we set out to. In particular, they all perform polynomial work per edge in the worst case. The best algorithm we know of is that of Ferragina and Lucio, which performs n log 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 n log m over n work for each batch update. Note that this bound holds regardless of whether you're inserting one edge or many edges. So for small batches, this performs much more work than simply using the single update algorithm sequentially. So our goal is to improve on that. So before we move on, of course, we should talk about the way we're going to analyze algorithms is in the work span model. The work performed by an algorithm is the number of instructions it performs in total across all parallel processes, and the span is the length of the longest sequentially dependent chain of instructions, also known as the parallel time in some models. Details of the model aren't super important because we're not going to be talking about any really low-level details. So just know that we're interested in shared memory algorithms using the work span model to analyze our algorithms. Okay, so the single update algorithm in the sequential setting is very classic and very nice. So say we have an MST and we wish to add a new edge to the graph. And we want to know, does this actually change the MST at all? If so, this edge will be inserted into the MST, and then another edge will have to be deleted to make up for it. How do we figure out which edge that should be? So it's quite simple. All we have to do is we look at the new edge and we look at the cycle formed by inserting that edge. Then all we have to do is look for the heaviest edge on this cycle. The heaviest edge is the one that's going to be removed. Of course, if the heaviest edge happened to be the newly inserted edge, we simply don't insert it. Otherwise, we insert it, we remove that heaviest edge, and we now have our new minimum spanning tree. So the key ingredient that we're going to make use of for our parallel algorithm is parallel tree contraction and parallel rate compress trees. So parallel tree contraction is a technique by Miller and Reif that takes an input tree and then produces a sequence of progressively smaller trees consisting of a subset of the previous tree. In each round you remove some independent set of vertices from the tree until you eventually end up with a single vertex. It turns out that this is really useful for designing dynamic graph algorithms. Ajar et al. Developed a data structure called Rake-compress trees, which use tree contraction and as a byproduct of that produce a dynamic tree data structure capable of supporting lots of useful queries. And very recent work by Jar et al. Developed a work-efficient parallelization of rake-compress trees. So we're going to be using that as an ingredient in our algorithm. So a brief overview of how tree contraction rake-compressed trees actually work. With tree contraction, we start with an input tree, and on every round we remove some independent set of vertices. In particular, we remove leaves, and we remove some random independent set of vertices that lie on a path of degree 2. So we may remove the following vertices in the first round. In the second round we remove some more. Eventually we may have a single edge left, in which case we remove one of the vertices arbitrarily, and finally we remove the last vertex, and what we end up with is this sequence of progressively smaller contracted trees. Now, how do we use this to get efficient dynamic tree algorithms? Well, the key here is to use the idea from rake-compressed trees, which is to interpret the tree contraction process as a recursive clustering. In particular, we can say that whenever a vertex is deleted during tree contraction, that it should merge all of the clusters adjacent to it. Initially, we assume that all vertices and edges are sitting in their own clusters of size 1. So every time a vertex is deleted, it merges with its surrounding clusters, like so. Next time another set of vertices is deleted, they merge their surrounding clusters, like so, and again until we hit the final remaining vertex, in which case everything is merged into a single cluster. Since it can be shown that parallel tree contraction takes log n rounds with high probability, this recursive clustering will have log n height with high probability, making it great for performing parallel divide and conquer algorithms over trees. Using techniques for dynamizing this process, we then obtain a useful parallel dynamic tree data structure, which will be of great use to us. So now we can talk about our main results on parallel batch-incremental MSTs. So the key ingredient that we came up with is this data structure we call parallel compressed path trees. Similar ideas have shown up before and been used in other algorithms, both for MSTs and algorithms that have nothing to do with MSTs. But they've all been in the sequential setting, and none of them achieve the work bounds as good as the data structure we're going to design here. So the motivation here is to think back to the sequential setting. When we insert an edge into an MST, we invalidate the heaviest edge on the cycle that it formed. In parallel now, we're in the batch setting, we're going to be inserting multiple edges in parallel. How do we determine which set of edges is invalidated? Because for every new edge inserted, we have to invalidate some corresponding edge. So we need to both make the decision of which of the new edges inserted to the graph become part of the MST, and which of the edges of the old MST are going to get removed. Parallel compressed path trees will help us answer both of those questions. So the idea is as follows. We have some minimum spanning tree of a graph, like so, and we have a set of edges to add. Now remember, an insight from the sequential case was we wanted to look for the heaviest edge on the cycle induced by the new edge. This is equivalent to asking for the heaviest edge on the path between the two vertices that are the endpoints of the edge. So in the batch setting, we really want to ask a similar question. The natural generalization of that is to consider the endpoints of the newly inserted edges, and then to consider all of the paths possible between those endpoints. So this is all the possible paths between those endpoints. Now, since this subgraph could still consist of an arbitrarily large number of edges, what we'd really like now is a compact version of this that succinctly represents all the heaviest edges on the path. So what we can do is we can take this graph, and whenever we encounter a non-branching path, that is a path with degree 2, we can merge the adjacent edges into a single edge represented just by the heaviest edge that was previously there. This now gives us a compact representation of all the heaviest edges on all the paths between any pair of vertices of the newly inserted edges, which is exactly what we need. So now we can go back to our batch insertion. We have the following 3 edges. To determine which ones we want to take and which edges we want to get rid of, we now simply run a parallel minimum spanning tree algorithm on this compact graph. It will identify the best edges for the MST, and the newly inserted edges that were selected, those are the ones that make it in and are inserted into the MST. The edges that didn't make the cut, those are the ones that get deleted from the old MST. Now it's not too difficult to show that such a compressed path tree, if we have k marked vertices, that is k endpoints of newly inserted edges, the compressed path tree will have size order k. In other words, it will have at most order k vertices and order k edges. This follows from standard arguments about compact trees. This means that using a randomized linear work MST algorithm, we can compute the new MST in just order k work and log n span. So the only thing that remains for us to do is to figure out how to compute this parallel compressed path tree efficiently in parallel. And that's where parallel rate compressed trees are going to come in. So to do so, we start with our tree and we mark the vertices of interest. So these are the endpoints of the newly inserted edges. This example will just mark 2 vertices just so the example is small enough to fit on my slides here. And what we do now is we're going to use the recursive clustering given to us by the RC tree. We're going to start at the top level cluster and we're going to descend recursively. The trick to making this efficient is that whenever we descend into a cluster that doesn't have any marked vertices in it at all, instead of continuing to recurse down, we can immediately stop and immediately know the answer for what that cluster should look like in the final compressed path tree. Let's see some examples. So we have the following 3 clusters at the top level. The algorithm looks at the bottommost cluster and immediately identifies it has no marked vertices in it. Since this cluster has no marked vertices, and it doesn't lie between a pair of marked vertices, it can simply be ignored and deleted. You know, it won't appear in the compressed path tree at all. We now descend into the rightmost cluster because it does contain a marked vertex, and we look at the 3 corresponding subclusters. In the leftmost subcluster, the algorithm identifies that there is no marked vertex, so rather than recursing further and descending down the clusters, we can immediately deduce what this part of the graph should look like in the compressed path tree. Unlike the last case where the cluster was simply deleted, since this cluster actually lies between 2 vertices, it still needs to be in the graph. But because it has no marked vertices, it can't contain any branching paths, and therefore it's compressed down into just a single edge. The weight of this edge would be represented by the heaviest edge on the path between those vertices, which is recorded by the Rake-compress tree. Similar to before, these 2 clusters on the right don't have any marked vertices, and they don't lie in between any pair of marked vertices, so they just go away and we don't recurse into them. On the left-hand side, exactly the same thing happens as on the right-hand side. So we'll end up with a graph that looks like the following. And now we're almost there. The last step is simply to realize that we have this redundant vertex sitting in the middle. It has degree 2 and it's not marked, so it simply gets spliced out. And we're left with this single edge, which happens to be the compressed path tree of that example. There are a couple of corner cases and tricky details to worry about in the full algorithm, but that's a high-level idea of the main ideas. So to summarize, the high-level idea for parallel compressed path trees is we recursively traverse the Rake-compress tree top-down. When we traverse into a cluster that contains a marked vertex, we keep going. But if we traverse into a cluster that has no marked vertices at all, we can immediately figure out what that cluster should look like. It should either be deleted, or it should just be condensed down into a single edge, whose weight is given by the heaviest edge between the 2 endpoints of the cluster. Now, using properties of Rake-compress trees, we can show that this whole process just takes order k log 1 plus n over k work, and log squared n span, where k is the number of newly inserted edges, or equivalently the number of marked vertices, between which we care about the path weights. And this is really good, because this is at most log n work per new edge inserted, and in fact it's even better than that for large values of k. So we plug this in to our idea before for computing a batch incremental MST. When a new batches of edges arrive for the MST, We compute the compressed path tree with respect to the new edge's endpoints. We compute the MST of the compressed path tree and those new edges to figure out which of the new candidates should be taken and which should be thrown out. So the edges that were selected by the MST, they go in. Those that were not selected get removed. And overall, since we can use a randomized linear work MST algorithm combined with our compressed path tree algorithm from earlier, this whole process takes just k log 1 plus n over k work and log squared n span. And this matches our goal that we set out at the beginning, which was we'd like to do at most log n work per new edge insertion. And we can see that for small values of k, it's exactly log n work per edge. But even better than that, if k is large, as k approaches n, the work bound just approaches order n, not order n log n. So not only do we have matching bounds for the sequential algorithms for small k, but we also achieve optimal work bounds for large values of k as well. And the log squared n span is only a log n span higher than the current parallel algorithms that perform polynomial work per edge. So we've met our goals set out at the beginning. Now let's see what else we can do with this cool new data structure. It turns out that incremental MST is a really useful ingredient for solving sliding window dynamic graph problems. So in the sliding window model, we assume we have some infinite stream of edges incoming. And what we want to do is make queries about what the graph looks like over some window of those edges, so some contiguous subsequence of the edges. More specifically, we want to support two operations. We want to be able to add edges, just like the batch incremental setting. We can add a new set of edges into the graph. But now we also support the operation expire, which allows us to delete the oldest k edges from the graph. And of course, we want to support some kind of query while we're doing this. So we can see that this model strictly generalizes the incremental setting, where we can only add edges, but is just slightly less general than the fully dynamic setting, where we can delete an arbitrary set of edges. Instead, in the sliding window model, we can only delete the oldest edges. So here's a little visual example. We have an infinite stream of edges, and we maintain some window, which is between these L and R pointers. Add edges simply moves the R pointer to the right, adding more edges into the window, while expire moves the L pointer to the right, deleting some of the edges. So we show in our paper that we can support a wide range of queries using these tools. In particular, we can support connectivity, k-certificates, bipartiteness, cycle freeness, approximate minimum spanning trees, and graph sparsifiers. So for the purpose of this talk, we'll just talk about connectivity as a simple example. You can refer to the paper to see the full details and the other examples. So to solve connectivity, we utilize a property that was determined by Crouch et al. They showed that if you maintain a minimum spanning tree of the edges in the stream that have been seen so far, and you weight each edge such that its weight is the negative of its position in the stream, that is, the edges just come in with weights -1, -2, -3, -4, and so on, then you can determine whether U and V are connected just by doing a heaviest edge query on the path between U and V. Note that the heaviest edge corresponds to the oldest edge under this weighting scheme, which simply means to check if U and V are connected, you check what the oldest edge is on the path between U and V, and if that edge is no longer inside the window, then U and V are not connected. So this gives us a very simple algorithm for doing sliding window connectivity. And we just have to point out that since rate-compressed trees can support heaviest edge queries in log n time, this allows us to support those connectivity queries in just log n time. And using our tools for batch-incremental MST, we can support the add edges operation in order k log 1 plus n over k work for a batch of size k. Now we can make one simple extension to this, which turns out to be a useful ingredient in many of the subsequent sliding window algorithms. In many of those, we don't just want to know about the connectivity between pairs of vertices, but we want to know about the global connectivity. In particular, we want to know how many connected components the graph has. A simple observation here is that the number of connected components inside a given window can be deduced from n minus the number of unexpired edges that are part of the current MST. So in order to do this efficiently, we simply have to store the set of unexpired edges in a parallel balanced binary search tree. For example, we can use the one given by Blelloch et al. And sort them by their position in the stream. Then we can support add edges by just doing a batch insertion into the balanced binary search tree, which takes order k log 1 plus n over k work. And we can support the expire operation by just doing a single split on the binary search tree, since we always remove the oldest set of edges. This corresponds just to doing a single split operation on the tree, which takes log n time. And since we can maintain the size of the binary search tree in constant time, this facilitates querying for the number of components in constant time. And this turns out to be a useful tool for solving many of the pieces of that list of applications I mentioned earlier. So in summary, we've designed the first parallel algorithm for batch-incremental MST that does polylog n work per edge. All previous algorithms did at least polynomial work per edge in the worst case. We showed that parallel compressed path trees were a key ingredient in solving this problem, and we believe they may have uses in other applications as well. Finally, we showed how this algorithm can be used to solve sliding window dynamic graph problems, which to the best of our knowledge is the first time anyone has considered such a combination of ideas. Thanks for listening, and let me know if you have any questions.